before I go to this, let me quickly tell you that I can still write the dimension of area as m raised to the power of 0, l raised to the power of 2, and t raised to the power of 0. Hello viewers, I'm Mav Genius. You're welcome to my YouTube channel. Alright, today we're going to be looking at physics, the topic dimension of physical quantities. Alright, dimension of what? Physical quantities. This topic is very important in physics, as it borders around a very important aspect of physics, which is measurement, quantities, and units. Are we together now? Alright, so we're going to be looking at how to look at this topic, dimension of physical quantities. It is alarming that most students do not know what dimension of physical quantities is, and that is why I'm here. All right, and if you are new to this channel and you have not subscribed to this channel, quickly do that, kindly do that rather, okay, and then make sure you like the video, and then make sure you also drop a comment in the comment section. And if you have any question regarding to physics and chemistry, you can as well drop it, whether you are writing the UTME examination this year, or WAEC or NECO, the SSCE. You can also drop some questions in physics and chemistry that will be posing threat to you, because here we turn students to geniuses. All right, so moving forward, we are going to be looking at dimension of physical quantities. Firstly, we have to look at what a physical quantity is, because this topic stems from two important aspects: dimension and then physical quantity. We're going to look at physical quantity before we come to dimension. All right, so what's a physical quantity? A physical quantity is the property of a physical object or a physical system that can be measured or quantified. All right, the reason why it's called physical quantities, of course, from the word physical, the opposite of physical is spiritual. So of course it's not a spiritual quantity, because these are quantities that exist in the physical world that we can relate with. All right, and of course you should know by now that in physics, measurement is very consequential in physics. All right, so I haven't told you what is physical quantities. Before I go on to talk about dimension of physical quantities, I would like us to look at types of physical quantities. All right, so physical quantities are divided. These physical quantities, all right, they are divided into two. All right, so where we have the fundamental quantity, the fundamental quantities, all right, and the derived quantities, the fundamental quantities and the what? Derived quantities. All right, so fundamental quantities are actually the quantities in physics that are basic. They are the primary or basic quantities. They are independent. Okay, in other words, they don't need any other quantities to be what they are. They are the most basic and independent quantities from whence other quantities are actually derived. All right, and so if we look at these fundamental quantities, examples of them, I'm sure you must have known that by now. Examples of fundamental quantities are: you have mass, okay, then you have length, then you have time, temperature is there, okay, temperature. All right, we have electric current, not just any kind of current, but what? Electric current. Then we have amount of substance, and then we have luminous intensity. All right, so these are about 7 basic fundamental quantities we have in physics, and from these quantities all other quantities are gotten. All right, I won't forget to let you know that using the SI unit system, all right, the unit of mass is the kilogram, the unit of length is the meter, the unit of time is seconds, The unit of temperature, we have the unit of temperature, but the SI unit, actually I'm giving the SI unit. And so the SI unit of temperature here, I'm sure you might think it is Celsius, but it is Kelvin, all right? That's the SI unit of temperature. We're looking at electric current is in ampere, okay? Subsequent lectures are going to be looking at all of these one after the other. So that's why you have to stay tuned to our channel, because we have a lot of things up for you. Amount of substance is you measure the mole, all right? And then luminous intensity is measured in candela, and we call it CD. We use the symbol CD to represent this. All right, so these are the 7 basic fundamental quantities in physics that all students need to be aware of. All right, now moving to the other type of physical quantities that we have what is called the derived quantities. I'm sure from this from the word you can get the meaning or have a tip of the understanding of what it means. Derived. All right, it's just like you know, in Nigeria we derive palm oil from palm fruit. So if there is no palm fruit, there is no palm oil. All right, so it means that one thing you have to know about these are dependent quantities. They are not independent as fundamental quantities are. They are derived. They are gotten from the fundamental quantities, and they are gotten from the combinations of fundamental quantities, which may include multiplication and division of 2 or more fundamental quantities. And we have a whole lot of them. They are much. Okay, so if you look at area is an example of derived quantity, because it is actually equal to length, okay, times length. All right, and maybe I should just give it as L so that we can just flow with it. All right, L times L. Okay, but sometimes students can say length times breadth. Okay, let's put it that way. Then volume is actually equal to length times breadth times height. And we also have speed. Speed is equal to distance all over time. Okay, the rate of change of distance per time is speed. Velocity having the same dimension as speed. Oh, talking about that, we'll soon come to that anyway. All right, so velocity having the same dimension as speed is just different from speed in the sense that it is a vector quantity, because we are making use of displacement, which is vector, and distance is a scalar quantity. All right, so we also have acceleration. Okay, and there are a whole lot of them. Acceleration is change in velocity, delta velocity all over time. Okay, and we also have force is equal to mass times acceleration. All right, mass and acceleration and what have you. There are a whole lot of derived quantities, and I would like you to make sure you get conversant with the derived quantities. Of course, they are all they are more than the fundamental quantities. So having said this, these are derived quantities, and because they are derived, they are gotten from the combination of 2 or more fundamental quantities. I would like you to keep this in mind, that talking about quantities, for instance, if you look at breadth, all right, breadth is talking about length. It's a distance between 2 points, all right, okay. And if you look at height is just vertical distance, so it's still length. I want you to note this, that breadth, height refers to length in physics. And also, if you look at distance is also length, because to measure distance you have to use the length. Okay, also you have to know that displacement also talks about length. All right, all of these are written in terms of length. So you can see now that area, if we take breadth to be length, that area is derived by multiplying 2 lengths, and so we got area, and is a derived quantity. And if you look at volume is length times breadth times height. If we take breadth and height as length, then it becomes length times length, and that is also a derived quantity. Then if you look at speed is distance over time, and if we take distance as a fundamental quantity of length, then we have it that speed is a combination using division to division between length and time. That's if distance becomes length. All right, and then also velocity is displacement over time, We have already said that displacement also implies length, and velocity is gotten from division between this length and time. You see why they are called derived quantities. And then acceleration, of course, if velocity is derived and time is a fundamental quantity, velocity is derived, of course acceleration which contains velocity will also be derived, because we derive velocity, and so it is part of the formula of acceleration. All right, and we also have force is mass times acceleration as well. So these are examples of derived quantities. All right, one thing I would like you to keep in mind is that there are no should I say, there are no direct formulas for the fundamental quantities. However, there are, for these things I've written, makes for the formulas of the derived quantities. So that is when I can ask you, what's the formula of area? You tell me the formula of area is length times breadth. That is going for the derivation of area. Are we together now? Okay, and then volume is length times breadth times what? Height. And so that's the formula of volume. Speed is equal to distance over time. That's the formula of speed, because this is the formula gotten from deriving speed, deriving the derived quantities. Are we together? Now, one thing I want to help you to do is how to, even though we have fundamental quantities, quantities are measured in units. Are measured in what? In units. So if we have fundamental quantities, then we should also have what? Fundamental units. All right. So fundamental units are the units of the fundamental quantities, and if fundamental quantities are actually independent, that simply implies that fundamental units will also be what? Independent. Okay, and so let's look at, if you're looking at derived quantity, you see that it is also measured, all quantities in physics are measured in units, and so we also have what? Derived units. Derived units, they are the units of the what? Of the derived quantities. And so if we want to get the SI unit, the what? The SI unit of the derived quantities, then we have to make use of the SI unit of the fundamental quantities that makes for that particular derived quantity. I don't know whether you get what I mean. I mean, if you want to get the SI unit of a derived quantity, now you have to make use of, let's say, derived quantity, let's say speed, for instance, and you want to get the SI unit of speed, then you have to use the SI unit of the fundamental quantity that make up for speed. And of course, distance is length, and so you can use the unit of what? Length, and the unit of time. When we combine them the same way, the quantities that makes up speed, then we get the unit. What I mean? All right, so if I want to get the unit of area, you see that I'm going to do length times breadth. All right, and so the unit of length is meter, times breadth is also length, and so it's also meter. So everything will boil down to give us meter squared, and that's the SI unit of what? Of area. In the same way, we can also get the SI unit of volume. That will be meter times meter times meter, and something multiplied twice will give you in cubed. That's meter cubed. All right, maybe I should bring this down so that you clearly see other ones as I will be deriving them. So now let's get the SI unit of speed. Okay, speed, we have written that is distance over time. Taking distance to be length, the SI unit of length is what? Is meter, and the SI unit of time is what? Seconds. And so we're going to say that the unit of speed is meter per seconds. That word per is the division. All right, so meter per seconds. And which other way can you write this? You have meter per seconds this way. I can write this as meter times 1 over seconds. All right, from indices we have something called negative index. If, for instance, you have a raised to the power of minus x, the solution to this is the reciprocal of the base, all raised to the positive power. Okay, so if I put 1 over, remove the minus sign, and it means that if I actually have this, I can rewrite this to be this. So what the power of s here is 1. So another way to write this, you can guess that, right? Okay, so that's meter times, from here, s raised to the power of negative 1. and if I join them together, it gives me this, and this also means what? Meter per second. They are the same thing. All right, so that's for speed. And if I want to go ahead to get the SI unit of velocity, of course, SI unit of velocity is actually displacement over what? Time. Most time we take displacement as S, okay, over T, also distance as well. All right, so if we want to derive the units, the unit of displacement is what? Is in terms of length. So the unit is, SI unit is meter, over time is also seconds, and of course this will give us meter per seconds, or the same way I've written the other one, per seconds. So these are how if you can derive a derived quantity, you can as well get the derived units of the derived quantity just by substituting each quantity by its unit, and that will give you practically the derived units of the particular derived quantity you are talking about. All right, so let's move to the next one, acceleration. If I want to look at acceleration, see, acceleration, okay, it's usually denoted by small letter a, is equal to change in velocity over time. Change in means final minus initial, and so if I say final velocity minus initial velocity, it will as well give me what? Velocity. All right, so it means that you can just write that for the purpose of deriving the unit of acceleration, we can write that acceleration is equal to velocity over what? Time. Subsequent lectures, we're going to be looking at all of these one after the other. All right, so we are now going to move on. We have derived the SI unit of velocity, which is what? Meter per second, but is divided by time. So this is velocity, and this is a division. Then I'm going to write seconds. That's the unit of time. All right, so to simplify this, I'll write meter over seconds. I'll change the division to multiplication and do the reciprocal of the second. That will give me 1 over s. If I multiply everything by multiply the numerators and multiply the denominators, I will have m times time to give me m, and s times s will give me x squared. All right, so we can call this meter per second squared. And you know what, if you can actually derive these units, it will help to go a long way for you to understand rather dimension, how to get dimension. All right, so this is just a brief introduction to physical quantities. All right, these are quantities that you make use of in everyday life. These are quantities that you use in measurement, okay, and they are divided into fundamental quantities and what? Derived quantities. And so all of this is what we can say that we have at this moment. All right, so the next thing we are actually going to look at is now dimension. What is dimension? All right, so I'll just have to clean the board. So if you are new to this channel, if you are watching me, why not like the video and hit the subscribe button so that you can always get notified whenever our undiluted science lectures are being posted. You can trust us with any of your science subjects, which includes precisely physics and chemistry, because these topics, or these subjects rather, pose a lot of threat to students. All right, moving further, dimension of physical quantities, which is actually the topic we want to look at. Dimension. So we have looked at the word physical quantity. We have to look at the word dimension. What do we mean by dimension of physical quantities? Most students and even teachers, if I may say, do not understand the meaning of dimension of physical quantities. Dimension, of course, dimension means so many things in different fields of study. But in physics, dimension of physical quantities is actually a way of relating other quantities with the fundamental quantities. All right, we are looking at how other quantities are related to the word fundamental quantities. That is dimension of physical quantities. We want to express other quantities in terms of the fundamental quantities. Like we want to break down derived quantities in terms of the fundamental quantities, meaning that we want to break them down so that we now have the fundamental quantities to use to explain them. Are we together now? Yes, that is dimension of what? Physical quantities. Now, in practice, in practice, dimension of physical quantities is actually the power, the powers to which the fundamental quantities are raised to get other physical quantities. Are you getting me? All right. The are the what? Powers to which the what? Fundamental quantities are raised to get the derived quantities. And quickly, before I will talk more things about dimension, because we have to look at the application of dimension, one of which is dimension of physical quantities is used to test the validity of a particular physical quantity. All right, we use it to test if the physical quantity given the equation of the formula, if that formula actually is valid. Okay, that's one of the applications which we'll be looking at in a short while. But I have to move further. Remember that under dimension of physical quantities, what we are actually looking at is the fundamental quantities. All right, the fundamental what quantities is the fundamental quantities are what we are actually looking at. And so I forgot to let you know that there are three most basic fundamental quantities. Even though we have 7, there are three most basic fundamental quantities. This is because these quantities are actually used more often in physics and in calculations. Most of the time, problems that you come across will be featuring these three quantities. Okay, they are always there, and they are what? Mass, length, and time. All right, mass, length, and time. All right, now under dimension of physical quantities, of course, we are talking about expressing other physical quantities in terms of the fundamental quantities, and these are the three most basic ones that will be used. All right, so what we'll do is that we are going to use a letter to denote each of these fundamental quantities, each of these basic fundamental quantities. That to take note of this, that we are not using their units. Most students will have to we actually make things complicated by trying to use the units. No, we're not using their units. We just use a letter, okay, to denote each of these quantities. All right, and so in dimension, conventionally we use what? Capital letter what? M. Okay, I should just tell you that we use the first letter of each of the fundamental quantities. All right, so if I choosing capital letter M, this will be what? Capital letter L, and this will be capital letter what? T. This implies that anytime you are doing fundamental dimension of fundamental quantities or other quantities rather, you have to, wherever you see mass, you have to replace mass with M. Wherever you see length, and I've actually told you I've only showed you some of the quantities that are related to length. When you see them, just take them as length. I've told you that you have distance is there. All right, you have displacement is there. They are all lengths. Okay, students usually get confused with this. All right, we also have breadth, even width is there. We also have width. Okay, we have height. These are all what? Length, because they are in the dimensions of length. So if I ask you what's the dimension of distance, dimension of distance is what? Is length. Dimension of displacement is what? Is length. Dimension of breadth is length, and all of these are length. So don't get it twisted. And so moving further, this mass, M, length, L, and what? Time, T. Now, having said this, for us to get the dimension of any physical quantities is as simple as ABC. All right, so what you just do is to help yourself by remembering the formulas or the equations for each of the quantities that you will be asked to get their dimension. All right, so having said this, maybe let me use this part of the board to try to do it. Now, moving further, you have that what? Let's look for the dimension of area, for instance. Area is actually equal to length times what? Length. All right, so what I'm going to do now is that since I have area made up of what? Length, I'm going to do that area is what? Length times length. So what I will do, I will replace, to get a dimension of area, I will replace length with the symbol for length, and that is what? Capital letter L. So I will use capital letter L, all right, times capital letter L for clarity purposes, I think let me write this as length times breadth. Okay. All right. So length is length, this is it, and breadth, I've told you, breadth is also length, and so L times L will give me what? L raised to the power of 2. So we can write that the dimension of area is equal to L raised to the power of what? 2. And that's just it. Super simple. You know, some students might be thinking you're going to be doing a whole lot of things here, but that's just it. As simple as that. If you can remember the formula or the equation for any other physical quantities, then what you just need to do, the job you just need to do in dimension is just to replace that particular quantity with that particular fundamental quantity of which the other quantity is made up of, with what is denoted by, and that's it, area. All right. So if I write that volume is equal to length times breadth times height, length times breadth times height, well, I'd like you to pause the video and give it a try. Okay. All right. So if you have done that, you know, length, of course, is connected to L. Then down your times. Breadth is under what is connected to what? Length. And so we're going to write it as what? L, then times. Also, height here is the L. All right. So L times L times L is equal to L cubed raised to the power of 3. And you know what? That is just the dimension of what? Volume. Super simple. That is it. Dimension of physical quantities. We are trying to express other physical quantities in terms of the fundamental quantities from which they are what? They are derived. So having said that, I think we should do some few more examples under this. Let's look at the dimension of speed. Speed is equal to distance over what? Over time. All right. Now, before I go to this, let me quickly tell you that I can still write the dimension of area as m raised to the power of 0, L raised to the power of 2, and T raised to the power of 0. Remember that in dimension, we are trying to express the fundamental quantities in the other quantities rather in terms of the word fundamental quantities. So if I want to include mass and time, even though area has no dimension for mass and time, then I can still have it this way. Remember, I had told you that dimension of any quantity is also the power to which the fundamental quantities are raised to. Yes, to get that quantity. So you know that anything raised to the power of 0 is actually equal to 1. And so if we take that this is 1 times raised to the power of 2 times 1, everything will boil down to give us what? Raised to the power of 2. All right. So having said that, you just know that you can also have this way. All right. And with that, we also have that the dimension of volume is also equal to what? M raised to the power of what? 0, L raised to the power of 2, T raised to the power of what? 0. Yeah, L raised to the power of 3 rather, T raised to the power of 0. Because everything you see boil down to give you 1 times L raised to the power of 3 times 1, and you see have the L raised to the power of what? 3, and it's the same thing. So if that is the case, we have it that way. Are we together now?